Thank you very much for inviting me to speak here. It has been really a great pleasure, this whole conference. I feel like I've learned so much. It's been really a valuable experience. So I'm going to give an overview of multimodal localization and mapping and how we are trying to use distance geometry in this setting of mostly robot localization. And this is really joint work with many of my colleagues at LCAV in EPFL Switzerland. And yeah, I will be including some of their works as well. So what is the setup that we're looking at? Excuse my bad drawing skills, but this is the kind of simplified view of what we're trying to solve. So we have a robot or some smart device in an environment. So we're looking mostly at indoor environments. And we're trying to find out if the robot can localize where it is and also find something out about its environments. And the way we do this is you can think about having some devices, like here we have a Bluetooth beacons, we have some Wi-Fi access points. Also, you can think about the robot having kind of eyes or cameras and ears, so it can hear sound, and mouth, so a speaker, so it can emit sound. And the general question we're trying to answer is, can you characterize your environment and the robot location based on these multimodal measurements? And just to put this work a little bit into context, so I made this simple diagram where you see different kind of research areas in robotics. And we have on the x-axis how much we know about our environment. So going from nothing to some sparse knowledge like anchors or access points to very rich knowledge like light field or the actual point cloud of the 3D of the environment. And then on the y-axis we have how much we know about the device location. So if we don't know anything, then we're in this interesting field of simultaneous localization and mapping, where you're trying to simultaneously find both information of the surroundings and the location of the robot. And if we know something, either sparse or rich, about the environment, then we're in the indoor or general localization setting. If we don't know, just for completeness, if we don't know anything about the environment, but we do know the pose, then I guess we're more in the kind of stitching maps together or doing 3D and light field reconstruction areas. And then finally, I mean, why do we even want to solve all of this? It's because once we know the device pose and we know the environment, then we can start doing all these interesting things. Like then we actually get to the robot applications where the robot can execute certain tasks, do motion planning in the environment and so on. So I'm going to talk about these two areas mostly. And maybe now to put this, and sorry, this should have been before actually. And I'm going to use a very simple example, so kind of an abstraction of our problem, where we have a robot or a device moving on a path, and we have some anchor points, we have some walls of which we might know or not know the position. So if it's unknown, I will draw it in blue. If it's known, it is drawn in red. And then we get some measurements drawn in green, and we try to reconstruct everything. Then now, to put this a bit into the context of distance geometry, so we think that this is an interesting research area because it feels like these two fields have grown kind of independently. So we have on one side the probabilistic robotics point of view where quite often we use heuristics. It comes from practice. Many of the methods are very practice-oriented, and they actually work with real robots. And quite often we use mostly range or bearing measurements and relative measurements between, so kind of an estimate of how the robot moves. And I added these two things in blue after the workshop because I think maybe we can also say that in robotics, usually distances tend to have very high variance and bias. So we have extremely noisy data. And typically we look at few points. So I'm not looking into the visual SLAM, which would be with cameras where you have thousands of points. But we're looking more into acoustic SLAM or Wi-Fi, Bluetooth-based SLAM, where you really have only a few anchor points. So this is kind of the probabilistic robotics field. And then distance geometry comes from a different background, where quite often we're trying to find a deterministic structure of our points. It comes more from the theory side. We mostly use Euclidean distances by definition of the distance geometry problem. And then also, we have seen also in the last few days that quite often we are interested in the problem where we have perfect distances, which is already an interesting problem, or we have distances given in intervals, which is not relevant in robotics because you never have perfect distances. And then also, if we look at the molecular structure application, we really have thousands of points, while we are just looking at a few, like 10 order of tens of points. So our research tries to kind of connect these two areas and bring in some of the probabilistic side into distance geometry and the other way around. Now, I'm going to talk about 4 sub-topics, and they can all be seen kind of like generalizing the distance matrices to something other than point-to-point distances. So I will talk about coordinate differences, which arises when we have distances and angles. Then I will talk about point-to-plane distances, which arises when we measure distances from planes, like walls, to points. So this is in the SLAM setting because we assume that we don't know where the anchors and the walls are, and we want to localize them while we are localizing the robot. And then I'm going to talk briefly about the localization setting where we have fixed anchors. So here, for example, sparse anchors. And then I want to talk about what happens if we have very sparse distance measurements. So if, for example, at each point along a trajectory, we only measure one distance. And then in the end, I'm going to talk briefly about a real system that I'm working on, as in an actual indoor localization system that should run on a smartphone in a real building, and what are the kind of challenges that we face there. So I will start with this. Excuse me. And so the reason why we started looking at coordinate differences is because we were looking at the microphone calibration application. So you have an array of microphones. These little symbols are the microphones. And you want to find out where they are relative to each other, given some signals. And if we're in the near field, so that means that speakers and microphones are relatively close to each other, then I don't have to convince you, I think, that this is a classical EDM problem. So we kind of, through some sound pulses, we can estimate the distance, and then we can do matrix completion, denoising, and reconstruct the point sets. While when we are in far field, we have something slightly different. So here, imagine that there are microphones at each of these points, and we have speakers in two known directions, and they are so far that the incident acoustic waves seem almost planar. So we approximate them to be planar when they arrive, and in particular parallel to each other for each different sound source. And then the question is now, here we don't have Euclidean distances anymore in the sense that we had here. So what can we do here? And it turns out that you can actually reformulate this problem in a coordinate differences framework. So what we are given is we know at what time emitted sound pulse here arrives at each of the points. But we don't know when it was sent, when the signal was sent. So what we effectively measure is this differences between times of arrivals. So I call these here like x12 for the time difference that of the signal between anchor 2 and anchor 1 in this example. And the same thing we can do for the other direction. So I call the directions phi 0 and phi 1 here. And now the question is, what can we reconstruct the coordinates with this information? And the same problem actually arises in a maybe more common framework, where we have distances and angles. And I think it has also been mentioned in previous talks that this can basically also be written like a coordinate difference problem, because if we have the distance and an angle, then we have kind of this vector, or an like edge vector, or however you want to call it. And we can then do the projection of this vector to arbitrary directions. In this case, it's convenient to use x and y. And then given these two projections, we can again try to solve this problem on the coordinate differences and then reconstruct the 2D locations. And how do we do this? So we thought it would be nice to introduce something like EDMs, but adopted to coordinate differences. So it's exactly like an EDM, only that now our distances are differences, so they can be positive or negative. And we put them into this matrix, which will now be anti-symmetric. And once we have this matrix, we can try to reconstruct the points like in the EDM setting. And it's easy to see that the CDM has this form if x contains our coordinates in 1D. And then what we measure in practice is a corrupted CDM, where we have some missing entries which are defined by this weight mask W. And then we have some additive noise, independent realizations. And the way we solve this problem is actually quite simple. So you can, if you write this in if you write the least square problem to estimate x given c tilde, then you can solve this problem. And this is actually, you can write this as a set of linear equations and just solve this set of linear equations. And then the reconstruction from CDMs then becomes quite simple, because...
It was a minimization of a norm. Why is that a set of linear equations? It was an optimization problem, no?
Yeah, so it's an optimization problem, but it turns out that the solution to this problem is actually, like, if you can differentiate this with respect to x, and you will get a set of linear equations, and solve the set of linear equations. And there are some subtleties which I don't go into detail now, because you have to fix translation, because it's invariant to translation. So and I'm actually showing this here. So when then you want to go back to 2D, you can solve the problem in both directions, x and y, which gives you the coordinates. so you construct CDMs, and then you get the coordinates from the CDMs, where you had to fix 1 point because it's invariant to translation. So you kind of lose this degree of freedom. And then generating R from X and Y here is super trivial. It's just, those are basically the coordinates of your points. But then what is a bit more interesting is when we go to higher dimensions. So you could think about not just projecting to 2 directions, but we project to many different directions. For example, in the microphone array calibration, I was showing just 2 sound sources, but we could have n sound sources and project to all of those. And then then the problem becomes a bit more interesting. And so we have shown that if the number of directions equals the dimension of your setup, so this is the case here where we have 2, then solving the problem in X and Y and then reconstructing the points from that is equivalent to just directly solving finding the global 2D solution. While if we have more than D projections, there's this equivalency is only holds in certain cases, depending on which measurements here you're given. And we are going to publish this in the paper called Coordinate Difference Matrices, which is currently in submission. So this is as much as I wanted to say about coordinate differences. Now, I would like to go a little bit into point-to-plane distances, although as a disclaimer, it's not my expertise. So I will have to refer you to my colleague for detailed questions. But I try to, for the completeness, I try to give an overview. So this problem kind of arose in the lab maybe 5 years ago or more, from the question, can we hear the shape of a room? So if you put some microphones, you have a microphone array, and you put it into a room, and then you have a speaker, then if the speaker emits some sound sources and the microphones hear the echoes, so hear both the sound from the sound source and from the echoes of the walls, then can you actually guess the geometry of your room? And so this was work done by Ivan Dokmanic mostly in our lab. And the answer was yes, you can. So this led to this paper, Acoustic Echoes Reveal Room Shape. And the main ingredient for this method is what we call a room impulse response. So this is visualized here. You have speaker emitting a sound, and the microphones hear both the direct sound and also the echoes from walls. And you can use what is called a virtual sound source model, where you can kind of, each speaker has also a virtual, each microphone has also a virtual microphone, which is simply the reflection along the wall. And then what you will hear is both the direct path and the path to this virtual source. And you can visualize these things in what we call a room impulse response. So this is basically over time, the amplitude of the sound heard for each microphone and from each wall. So here the green one would be the direct path, red is the reflection from wall 1, and blue is the reflection from wall 2.
Avoid interference.
As I think we ignore wall interference. Yeah. So yeah, in practice, I guess you can ignore it if you're only interested in the distance in the end. So this problem was kind of solved, I guess. I mean, it worked in many rooms and for different configurations. But then what we were interested in is can we do the same with less? Because what we did here was having kind of 5, I think, or 7 microphones and a speaker, and you have to know the locations of the relative locations of the microphones, and our idea was, what is the minimal kind of setup where you can still do the same thing? And one natural choice was to have collocated sound source and microphone. So here you would have a speaker and a microphone in each point. And so it's quite obvious that if you just had one point in a room and you measure the echoes, you cannot reconstruct anything from that, or like it's not uniquely defined. But then what happens if you start moving these collocated microphone and speaker, and can you then say something about the geometry? And as I mentioned before, this is mostly work done by my colleague Miranda. And so what she introduced is this tool called point-to-plane different distance matrices, which basically capture the distances between the walls and each point. And so you can write it as a number of walls by number of points matrix. And you can show that if we call C an unknown offset from each of each wall, and then A contains the normal directions of all the walls, and X again contains the unknown points, then you can factorize PPDM point-to-plane distance matrix like this. And you can use this kind of tool to both show uniqueness of reconstructions and to do the reconstructions. So then again, we try to solve this when we have noisy distances with the least squares problem. And here it turns out that because you have this unknown offset, it's actually easier to write this again in this kind of coordinate difference setting. So then we get rid of this C by using coordinate differences rather than absolute distances. And then you can solve this in an alternating way. We can solve for X and A in an alternating way because it's convex in both if we fix one. And there are some interesting results on the uniqueness of reconstructions. So if I come back to the original question, we wanted to know if with this kind of minimal setup, we can still uniquely define the trajectory and the room shape. And it turns out that it's not as easy, actually. So the three trajectories that you see here, so the trajectory is linear. The point is some polygon of degree 4. And you can see that all these three configurations actually have the same PPDM. So they all actually are not distinguishable from each other if you're only given distances. And there is a whole, Miranda did a whole analysis of these, what she calls kind of equivalency classes in both 2D and 3D, where you can show for certain setups of walls, like all parallel walls, so this is more like a abstract concept, to parallelograms, arbitrary shapes in 2D. What are the kind of trajectories that you can or cannot uniquely reconstruct? So there are more details in this paper here. So this was the part about SLAM, so trying to find both locations of the robot or device and the walls at once. Now I want to talk a little bit about the localization case, and first about the case where we have sparse distances. So we started looking at this problem because we have this little robot. Actually, this is like this size robot. it has 2 wheels, both independently motorized, and some intelligence up here. This is just a passive omnidirectional wheel. And we want to do localization experiments with this robot. So the robot moves in a trajectory in a room, and we want to reconstruct its trajectory. And what we do for this is we mount some devices on top here. So we are using, for example, Wi-Fi round-trip time. So from Wi-Fi signals, you can get the time it took from the receiver to you and back. And from this, obviously, you can infer a distance. And these distances tend to be relatively accurate. So this is actually more accurate than what we often have in indoor localization. But then still, the kind of problem is that the robot, as it moves along this trajectory, it will always kind of see like one distance measurement here and then one distance measurement there. It's not the classical EDM problem where you have many distance measurements at once and you try to reconstruct the whole thing. So in a sense, we're sampling over time rather than in space. So to visualize this a bit clearer, hopefully. So in the kind of the theory that we are most familiar with, quite often you have a lot of distance measurements, or at least enough for your reconstruction to be well defined for each point. And then you could kind of independently reconstruct each point using these measurements. While in practice, it might be that at each point you actually only measure one distance. So of course you couldn't independently localize each point, but maybe, so our question is, could we still do something with this? Could we try to still reconstruct the trajectory from such measurements? And the answer, so what we have, this is very recent work and it's very much work in progress, so I will mostly give like a sketch of what we're doing. So we try to solve this problem by imposing a trajectory model. So we call this, this trajectory model has some basis coefficients which I call fk, and it has, the basis vectors are fk, and the coefficients I call ck, and we have big K of them. So then in a sense, instead of here having n points to localize, if we say we have n time instances, we reduce our problem to only k coefficients and k times t coefficients. So it should be an easier problem to solve. And just to show the actual problem, so we introduce the matrix C with all the unknown coefficients, and then we also sample uniformly in time. So n here is our time index, and big T is the sampling period. And we introduce this vector Fn. Then we can show that we can rewrite the problem of finding the trajectory as such. So we try to find the coefficient matrix C such that all these different distance constraints are satisfied. So this is our anchors, and this C times Fn, if you do the calculation, is the discretized form of R of t. So this would be R of n times capital T, what you have here. So this is the problem that we're trying to solve. And fortunately, I don't have to explain this because Professor Liberti showed in his tutorial that you could solve such problems with semi-definite relaxation. So we can introduce this new variable z, where we basically have identity and then our unknown coefficients C and C transpose. And then we have use this trick that we just replace the quadratic term in C by a new variable L, which is here in the bottom right corner. And then we try to optimize for Z. So this is a relaxation of the original problem. And we're currently looking into when this relaxation is exact, and also how many measurements we need, and where do we need these measurements for the problem to be well defined. So I guess this goes almost into rigidity problems, where we're trying to find out when is the graph that we're trying to reconstruct uniquely defined. And I just show you two examples. So as I said, this is very much work in progress, but two maybe surprising to you examples where it works or doesn't work. So here we have a polynomial trajectory, and here we have a band-limited trajectory. So I'm using two different kind of basis functions. And in green, I'm drawing which measurements we have. So these are all, in this case, perfect distance measurements. And so I'm looking at, even with perfect distance measurements, if these reconstructions are well defined. And it turns out that in this case, they are. So in green, overlaid in green, you see the reconstruction. So it's perfect up to numerical precision. But then in a maybe similar case where we have a bit fewer distance measurements, and we do exactly the same method, then it turns out that we get very degenerate trajectories. So, and obviously this is very far off what we actually did. So we kind of want to avoid that in practice. And we're working on finding both kind of lower bounds on how many measurements do we need to reconstruct this uniquely, and also starting, like, if we have, do we have a bound on if we have enough measurements, then it will actually be, we can be pretty sure that it will be, that we can avoid such degenerate cases.
There's something I don't quite understand in the motivation. So it seems like it should be the converse. You can control a robot, right? Mm-hmm. And maybe the robot is in an environment that you don't know anything about. Okay. So in that case, it's like, using the robots in order to hear the shape of a room, for example. But it seems you're trying to reconstruct the trajectory of the robot rather than the shape of the room.
Yeah.
So what am I misunderstanding?
No, it's absolutely correct what you're saying. So the idea is, in a sense, hearing the shape of a room with the robot is the example from before. So it's there we use these point-to-plane differences. While here we're looking more at more like an indoor localization kind of setup. So you can imagine.
You don't control, but it's moving according to certain bases.
Yeah.
And but you know the shape of the room, or you know whatever else, yeah. And then you want to know where the robot is going.
Exactly. So it's in a sense, you're right that we know exactly what the robot is doing, and this is actually convenient because we can use this almost as ground truth. Yes. Because we have stepper motors that are extremely accurate. So it's more about, we use the robot as a ground truth for some device.
I understand. This is also useful, but it's just
okay.
Like
it's a different, yeah, exactly. Okay, so this is all I wanted to say about this application. And then finally, I want to come to this real-world system that I'm working on. So this is a collaboration with startup and University of Fribourg. And we're trying to create a system that runs on a smartphone and can localize in real time where the smartphone is. And especially in GPS-denied environments. So just for context, so this is our building in EPFL where I'm working here on the 3rd floor. And this is the kind of environment that we have for now done our tests in. So it's a real environment, as in you have walls, you have obstacles, you have glass rooms here and all sorts, and people moving around potentially. And we're using technologies that are entirely smartphone compatible, which is actually quite a big limitation, because that basically reduces us to Bluetooth, Wi-Fi, IMU measurements, so inertial measurement unit, which gives you a relative, you can calculate from that relative movement, direction, and length. And we can use the smartphone camera, but we're trying to not use it too much, because that's basically a solved problem. If you could just scan your environment, then this is very much a very well-studied problem. So now what do we have? We have basically these very different kind of measurement modalities. And in addition to that, they're all extremely noisy. So you can think about now, instead of having exact or almost exact distance measurements, you have kind of a distribution of distance measurements. So, and the same thing here, you could imagine having an angle measurement, but actually you only know that you're within a certain range of that angle, and so on. So what we do in the system is we try to put all these measurements into one big measurements vector, and we might, so here I have all of them, but we might not have all of these measurements. And then we try, the question is how can we combine these measurements into a consistent estimate? And it's kind of an apple and pear problem, because how do you combine such different modalities? And the way we do it is by, instead of combining them directly, for each measurement modality, we create kind of a probability map. So for example, here we discretize the space, and then for each point in space, so this is 2D space, x and y, we find the probability that we are in each location, given that we have these Bluetooth measurements. So here the black points are Bluetooth anchors, and the white means yellow means high probability, and blue means low probability. And we can do this for each of these modalities. And the good thing is that now, if, for example, the Bluetooth measurements are extremely inaccurate, which they are most times, then you can see here that there's not much information here. Like, this is pretty much completely flat. So when we now combine all these three modalities together, then in the final probability map, Bluetooth basically didn't have any influence, because it got outweighed by IMU measurements and Wi-Fi, which tend to be more accurate. So if we have those, then Bluetooth kind of loses importance, and vice versa. So this is a desired property. And then I will skip this. So then, or only one sentence for this. So then solving the localization problem is, you can basically run a simple Viterbi algorithm. So at each time instance, we try to find the probability of each point, Ri, discretized point, given the measurements. And we can do that by calculating this maximum probability. And just a few results. So here, this is a system that is not smartphone compatible. It uses ultra-wideband anchors, which are designed for indoor localization. So they're extremely accurate. You can see in orange the ground truth, and in blue their estimate. And then this one is our solution. So you can see that it jumps around a little bit, but in general it captures the shape of the trajectory that we did quite well. And then I'm just comparing here to two only distance-based methods where we don't impose any of this probabilistic view. And you can see that here the results jump around much more because of this really high distance noise. This is not important. So to conclude, I have shown you kind of these 4 different research areas that we are looking into for bringing distance geometry closer to SLAM or SLAM closer to distance geometry. And there's still a lot to do, obviously, but so just like a few ideas of open questions. These coordinate difference matrices, we're quite interested in how they relate to EDMs, and does a lot of the theory that we have for EDMs apply to CDMs and so on. Then in the PPDM case, we're currently not using any time consistency between points, so it could be interesting to also there kind of impose some trajectory smoothness. We haven't validated these sparse distance method on noisy data, and our intuition is that it would probably be quite sensitive to noise, actually. So this would be another research direction to make this actually work robustly. And then finally, you might have thought that actually this real-world system that I showed you has nothing to do with distance geometry, which I agree with. So our idea here is to maybe try to bring in distance geometry more for outlier rejection, for example. So if you have many distance measurements, you can kind of find out if one of them doesn't match with the others at all because of the rank of a gram matrix or something like this. So we're looking into doing stuff like that. So that's it. Thank you.
Question before lunch.
Yes?
I have one question about that causing the differences that applications. I think you mentioned that and from figures that you use actually 2 microphones just to find out to emit some, like let's say in the far field to emit some wave.
Yes.
So do you always use 2 microphones, or do you use more microphones, and how many? Let's say what's the minimum number of microphones that you can use to make sure you get a reconstruction?
So we use. We find the slide. Here. Yeah. We actually, so
the speakers.
Okay.
Sorry, I mean speakers.
Yeah, so we used 2 speakers because we're here. I'm plotting the 2D. So then you only need you need D speakers. So if dimension is 2, D is 2, then you need 2. If dimension is 3, you need 3, because it's really like you're basically trying to find all coordinates. So if you're in 3 dimensions, you need 3 independent, linearly independent directions so non-collinear directions. And yeah, we have tried in 3D on real data, actually, this one. And then, so you don't want to only use 3 because obviously the distances are noisy, and the more you can get, the better. So what we do is actually the microphone array is on a turntable. So we're not moving the speakers, we're moving the microphone array, and then you can just kind of turn like angle by angle and get as many projections as you want.
Yes.
So for the last application you have, what's the probability model for the observations?
The probability model? We use, you mean the assumptions, or what kind of probability?
So beta is applied at the last stage to determine the highest state, right?
Yeah.
So what kind of model are you using to model the observations?
We're using, for now we're using Gaussian. For all modalities, we're using Gaussian. With maybe one subtlety that, it will take long. With one subtlety that the Gaussian for Bluetooth measurements is, so the variance is on the RSSI measurements, which is in dB, it's in dB meters, so it's in logarithm. So then when you convert that to distances, it's not a Gaussian anymore. It becomes a log normal distribution.
Okay, let's thank speaker again. Thank you.
Thank you.